with the Academy of Science and Technology. Today I am going to discuss an easy method for solving partial differential equation, and the method is method of separation of variable technique. See, by the name, in this method we are always separating the variables. See, in this method first we assume the solution. Let me illustrate this method through an example. So consider the partial differential equation: dou square z by dou x square minus 2 dou z by dou x plus dou z by dou y equal to 0. Clearly, in this equation, the dependent variable is z. Dependent variable is z. Here, x and y are independent variables. That we assume the solution as dependent variable z is equal to product of functions of the independent variables. That is, assume here the independent variables are x and y. So assume z equal to xy, where capital X is a function of x alone and capital Y is a function of y alone. Next, see, our assumption is z is a solution. So this solution satisfies the given equation. So you find dou z by dou x, dou z by dou y and dou square z by dou x square. And we know, see, this is a solution, so this satisfies equation number 1. So next we have to find these partial derivatives. See, we assume z equal to xy as the solution. So dou z by dou x. See, you can see capital X is a function of x alone and capital Y is a function of y alone. And clearly small x and small y are independent variables. So x contains only x. So dou z by dou x is x dash y, where x dash is dx by dx. Again, dou z by dou y. See, y is a function of y alone. So dou z by dou y is capital X into dy by dy, that is y dash, where y dash is dy by dy. Next, dou square z by dou x square. See, this is dou by dou x of dou z by dou x. That is dou by dou x of dou z by dou x is x dash y. See, only x dash contains the variable small x. So its derivative is, here y is a constant. So y is a constant and derivative of x dash with respect to x is the usual derivative and it is x double dash, where x double dash is d square x by dx square. Substitute these derivatives in equation number 1. Thus, we have this equation by substituting the derivatives in the given equation. Next, we have to separate the variables. That is, you separate it as a function of x alone and a function of y alone. So, see, from here you have to remove y and see, it is in separated form. In this you have to remove x. So you divide throughout by xy, then you can see variables are separated. So dividing by xy, we have x double dash minus 2x dash by x plus y dash by y is equal to 0, which implies see, now the variables are separated. See, this is a function of x alone and this is a function of y alone. We know small x and y are independent variables. So this equation is possible only if each is equal to a constant. So each equal to a constant k. So we can consider x double dash minus 2x dash by x equal to k, and minus y dash by y is equal to k. So we have two differential equations. See, these two equations are differential equations because x dash is dx by dx, x double dash is d square x by dx square. It is an equation containing derivatives, so it's a differential equation. Similarly, this is also a differential equation. Next, solve these two differential equations. By solving this equation, you will get what is capital X. From this you can find capital X, and from this you can find capital Y. See, our solution is z equal to xy. By solving these two differential equations, we will get capital X and Y. You put capital X and Y here, and that is the solution. Our differential equations are these two. Next, we have to solve these differential equations. Consider the first differential equation, that is say capital X dash is dx by x. Let capital D be the operator d by dx. So you can rewrite this equation as d square minus 2d minus k into x equal to 0. See, it is a differential equation with constant coefficients. That is, the coefficients are constants. So the method of solving such differential equations is you write the auxiliary equation, then solve the auxiliary equation. By the nature of the solution of the auxiliary equation, you can easily write the solution of the differential equation. See, this is the method. So here, write the auxiliary equation. Its auxiliary equation is, you replace d by m. See, its auxiliary equation is this one. Next is find the value of m. See, it is a second degree equation. You try to find the solution of m. M is two will cancel. So the values of m are 1 plus root 1 plus k and 1 minus root 1 plus k. Then solution of this differential equation, capital X is equal to C1 e raised to 1 plus root 1 plus k into x plus C2 e raised to 1 minus root 1 plus k into x. So now we got the value of capital X. Similarly, by solving this differential equation, we will get capital Y. This differential equation can be written as minus y dash minus yk equal to 0. That is, y dash plus yk equal to 0. See, it is a differential equation with the constant coefficients. Here the coefficients are 1 and k. Both are constant. So it's a differential equation with the constant coefficients. The method of solving is, you can rewrite it as d plus k into y equal to 0. Where capital D is the operator d by dy. Its auxiliary equation is m plus k equal to 0. So m is equal to minus k. So y is, say here we introduce the C1, C2, next arbitrary constant C3, and y is e raised to minus kt. This is y. So we have capital X and the capital Y. So general solution of the given partial differential equation is z equal to, see, z equal to x into y. X is C1 e raised to 1 plus root 1 plus k into x plus C2 e raised to 1 minus root 1 plus k into x into C3 e raised to minus kt. See, this is the general solution. Again, you can make some arrangements with the arbitrary constants. Here C1, C2, C3 are arbitrary constants. So you can again express it as, here C1 into C3. C1 into C3 is another arbitrary constant. Let it be C1 dash. C1 dash e raised to 1 plus root 1 plus k, root 1 plus k into x plus C2 into C3 is another arbitrary constant, C2 dash e raised to 1 minus root 1 plus k into x into e raised to minus kt. See, again you can replace C1 dash and C2 dash as C1 and C2 since these are all arbitrary constants. So we can consider the general solution of the given partial differential equation as this solution or the solution as z is equal to, you got an idea of solving a partial differential equation in variable separable technique. See, in this technique we start with a solution. See, you write the solution as dependent variable is equal to product of functions of the independent variables in the separated form. Next you find the partial derivatives which occur in the given partial differential equations from the solution, and since we assumed that the solution it satisfies the partial differential equation, you substitute these derivatives and you separate the variables. And you can see that is possible only if each is equal to a constant. Then from this concept you form differential equations. Next, by solving these differential equations you can easily write the solution of the given partial differential equation. In the previous example, the differential equations are equations with the constant coefficients. Next, let me solve another problem by this technique in which the differential equations are not with the constant coefficients. Consider the PDE x dou u by dou x minus 2t dou u by dou t equal to 0. Here the dependent variable is u and the independent variables are x and t. So we have to assume the solution as u is equal to capital X into t, where capital X is a function of x alone and capital T is a function of t alone. Next, in the given PDE, you can see the derivatives are dou u by dou t and dou u by dou x. So you find dou u by dou x and dou u by dou t. See, it is x dash t and it is x t dash. Next, substitute these in the given partial differential equation. So you can see x into x dash t minus 2t x t dash equal to 0. Next, separate the variables. So from this you have to remove t and from this term you have to remove x. So dividing throughout by xt. By dividing throughout xt you can separate the variables. So which implies x into x dash by x minus 2t t dash by t is equal to 0. Which implies x dash by x is equal to 2t t dash by t. Since capital X is a function of x alone and capital T is a function of t alone, both are independent variables. So this equation is true only for each is equal to a constant. Let it be k. So from this you can consider two differential equations. One is this equal to k and the second equation is this equal to k. Next, by solving these two differential equations we will get what is capital X and capital T. Next, you put the values of x and t in this equation, we will get the general solution of the given partial differential equation. We have to solve these two differential equations. Clearly, both are not differential equations with the constant coefficients. Consider this one. Say its coefficient is x and it is k. See, this coefficient is x. It's not a constant. So, you cannot solve this differential equation by the previous method. So, here x into, it is x dash is dx by x by capital X is equal to k. This implies dx by x is equal to k dx by x. Now see, it is in variable separable form. So by direct integration you will get the solution. So which implies integral dx by x is equal to integral, which implies log x is equal to k log x plus constant, let it be log c1. So which implies x is equal to c1 x raised to k. That is our capital X. Let's consider this differential equation. See, it's not a differential equation with the constant coefficients. So it can be written as by rearrangement you can rewrite it as this one. See, it is in variable separable form. So by direct integration you will get the solution. That is 2 log t is equal to k log t plus log c2. That is log t square is equal to log t raised to k plus log c2. That is t square is equal to c2 t raised to k. So we have to find t. So what is capital T? Capital T is c2 t raised to k by 2. T is c2 t raised to k by 2. Here we assume the solution as u equal to x3. So substitute the values of capital X and T in u, we will get the solution of the given partial differential equation. Hence the solution of the partial differential equation is u is equal to c1 x raised to k c2 t raised to k by 2. Again, since c1 c2 are arbitrary constants, you can replace c1 into c2 as c. So it can be written as u is equal to c into x raised to k t raised to k by 2, which is the general solution of the given partial differential equation.